Okay, so on Tuesday, we started to discuss the interrupts, and I said that before each executing each instruction, the processor first checks to see if any interrupt has been occurred or no, and then based on the interrupt, if there is an interrupt, it moves to like the interrupt routine. If there is no interrupt, it starts to run the next execute to run the next instruction. And here is the like the chart that we already discussed on Tuesday. Okay, but what if an interrupt has been occurred? What if we have an interrupt? First, we have when an interrupt is occurred, the processor moves like to first it detects the interrupt signal. If the interrupt signal is detected, the next thing that the processor does, and it's very important, it's saving variables and registers. Why processor needs to save variables and registers before going to the interrupt routine? It's because that after finishing the interrupt, it will be come back to like the program and continue the program. And if there are values in the like registers that are needed for the next instructions, we don't want to lose those information. So before running any interrupt procedure, the processor has to store all the variables and the registers in the memory and then start the interrupt routine. After saving the variables and registers, the processor, based on the type of the interrupt, look up the ISR or interrupt service routine address in the interrupt vector table. So each interrupt needs to be like treated in different way. For example, if it is dividing a number by 0, the interrupt should send the user a message that there and like zero division error occurred. If the interrupt is low battery, the processor needs to save unsaved works. So each interrupt has a different procedure, different orders. So first, the processor looks to interrupt service routine address in the interrupt vector to see it needs to go start from which address, and which address is for that specific kind of interrupt. After finding the address of the interrupt service routine, the processor places the address in PC, because we know that the PC is like pointing to the next instruction which is supposed to be executed. So by placing the ISR address in PC, the next instruction which will be executed, in fact, is like the first line of the interrupt routines. And after placing the address in PC, of course, the processor will branch to that routine because the PC is like now updated to the address of the interrupt routine, and then starts the interrupt routine. When it starts the interrupt routine, based on the type of the interrupt, it performs the work specific to that interrupt. So any interrupt needs to, as I mentioned, needs a different different tasks to be done for each interrupt. So those tasks will be performed, and after finishing the interrupt, it will be returned. Then restore the registers and variables which were saved, because at this moment the processor wants to continue the normal and original program. So at the middle of program, we move to the interrupt. And so at this point, when we come back to the original program, we need to restore all saved register and variables and branch to the like to the like the part that we left from that point. Okay, so this one is the memory, and we have different instructions. Okay, so it starts from address 0 up to address 4K. Okay, and let's say from address 0 to address 100 is like a program. We are running a program. So all these green highlights is the main program. And in part of the memory, let's say this is just an example. The numbers are like example, they are not exact numbers. So let's say address 1000 and address 1100. These are two interrupt routines. So at 1000, interrupt routine service, which deals with divide the number by 0, divide by 0, and which will let the user knows that the number has been divided by 0. The another interrupt is in address interrupt routine is an 1100, which is like low battery warning. Okay, low battery warning. So these two are in the like memory. So what when we like every time we want to upload or write a new program, we place our program in this part, not like in this part, because the second part are dedicated only for the interrupt. Let's say we are at this address 50, at this address, and one interrupt occurs. Interrupt. That interrupt is, for example, low battery interrupt. If the interrupt is low battery interrupt, what's gonna happen at this moment? The processor is going to save all variables and registers. Okay, and then jump to interrupt, jumps to interrupt routine service, which is ISR, not IRS. Interrupt service routine. So then jumps to the interrupt service routine for low battery. At this moment, the processor starts to like do some tasks based on what is in this location. After finishing the interrupt, the processor retrieve all variables and registers and moves to the next instruction and continue the next instruction from the point that she left the main program. Okay, so it's the way that any interrupt like get executed. Any question? Okay. If there is no question, let me move to slides. Okay, and one thing that I need to mention, so I remember I already posted the lectures on Sakai. Just an hour ago, I posted the last lecture we had on Tuesday, so you can just watch the lecture video on Sakai, and it I think that it helps if you like need to do some more practice. You can use the lecture and learn it. Okay. I said that some interrupts are we able to disable sometimes some kind of interrupts. We call them maskable interrupts. If you remember, I gave you an example, and I gave you like an example, like somebody knocking the door. We can just ignore it. So it's like maskable interrupts, and some interrupts are non-maskable interrupts that we cannot ignore those interrupts, and we have to process those interrupt service routines. Okay, now that we learned about 9 basic instructions on Mari processor, and of course we discussed the interrupt, we discussed registers, control unit, and we discussed the data path. It's time to have a real program. Okay, simple, super simple program. Okay, so here is a super simple program which consists of several lines. Line one, first line. First of all, we should notice that this program starts from address 100. Okay, it starts from address 100. As address 100, the instruction we place is load 104. Okay, load. If you remember, load had a opcode of 0001. So if we want to convert it to binary content, it will be 0001. 104, if we convert it to the binary number, will be this number. Okay, 0001 50101. So this is zeros and ones that we see here is like the binary code of the instruction load 104. And if we want to show it in the hexadecimal format, it will be 1104. This one is in the hexadecimal format. The second instruction, which is located in address 101, is called add 105. Add has an opcode of 0011, and 105 is like this binary number. So the hexadecimal equivalent for add 105 is 3105. The last line is store 106, the same story. The next line is line 103, which is halt. Halt has those kind of instructions that doesn't have an address field. The address field is 0, and the opcode of halt instruction is 7. So we place 7 in the opcode field, and the rest of bits are 0. So the hexadecimal equivalent for halt instruction is equal to 7,000. Any questions so far? Okay, so if there is no question so far, let's see what does this program do. I'm starting from address 100 up to address 103. So load 104 says that processor gets the content of address 104 and put it in accumulator. Then we have add 105. It means that gets the content of address 105 and add it by accumulator. Accumulator has a value of the address 104. So by running these two lines of programs, the content of address 104, the content of the address 104 will be added to the content of address 105 and will be placed in the accumulator. Line 102 says that store the accumulator value in address 106. So the accumulator, which is the total of addresses 104 and 105, will be stored in address 106. Okay, so now let's see what we have in addresses 104, 105, and 106. In 104, we have the value of 23. It's not instruction, it's just data. The value of 23. In 105, we have a value of FFE9. FFE9. And 106 is empty. After running this program, these two numbers will be added to each other and will be placed in this address. Okay, any question? Okay, so was anyone able to watch one of my videos that I posted online on the lesson section on Sakai? Okay, so because I got like a message from one of you that says that this student was not able to look to videos. So let me tell you one thing: you shouldn't go to resources. Just when you log in to a Sakai website, on the left panel there is a bunch of like buttons. The last one, maybe the last one, I'm not sure. It's called the lessons. If you click on the lessons, there you will see several buttons that each has a like date. Okay, the lecture date, so lectures and with date. If you click on any of those buttons, the lecture will be appear and you can see the video. So for this student that says was not able to load my videos, just try to access okay, yes, okay, so you got the answer. Okay, that's fine. So you shouldn't go to resources, just move to videos and watch the videos. Okay, and as I said, don't worry about the time. I give all of you, if you need, I give you extra time. Okay, so uh, so this instruction, this short program, in fact, added 23 and FFE9 and put it to 106. Who can tell me what is the like decimal value, decimal equivalent of FFE9? What number is that? Any idea? Let me give you a hint. If you remember, I said that Mari processor works in two's complement, and FFE9 has like leftmost bit, of course, is one, so it means that the number is negative. So we need to find this number with two's complement method. Can you find the number for me? I want 4 correct answers to move to the next line. Just try to find the decimal equivalent of FFE9. I got one answer. Okay, I got in the binary number. Of course, it's not. It doesn't start from with the 1, because if it starts with 1, it's again it's negative number. So I got it. Third answer, fourth answer, fifth. Okay, let's see. Let's do it together. Okay, that's enough. I got some answers. Okay, let's see what answers are received. I got 22. I got a binary number that starts from with 1. I got 65, 513. I have 61, 65, 512. I have again 65, 512. I have negative 23, and I have negative 65513. Okay, I have these answers. First thing, definitely those numbers, those answers which are positive are wrong, because I'm telling that this number is negative, because the like leftmost bit is 1, so the number is negative. Okay, so let's just find it out together. So first we need to complement this number. So if we complement this number, it will be 0, 1, 1, 0, 1, and 0, 0, 0, 0, up to 16 zeros. So this one is like the inverse of the number. And if we add it by 1, we will have 1, 1, 1, 0, 1, and zeros. So what is this number in by like decimal? So it is 2 plus 1 plus 1 plus 2 plus 4 plus 16. So 1 plus 2 plus 4 plus 16 is 23. 23. And because the number is negative, the answer is negative 23. Okay, so the answer given by one of you is correct, and it was negative 23. So we should add 23 with negative 23. What is the product? Of course, it's 0. Okay, so let's move on and see how does this program is executed. Here we have like a chart that shows like each instructions and the registers. The first instruction is load 104. Load 104. RTN, the like register language, okay, register transfer language, if you remember, was like a program which is consists of micro operations, and it shows the like data transformation in register level. For the load, what's going on in the load? At the beginning, so this each row is time. So let's say time 0, time 1, time 2, time 3, time 4. It's time clock cycle. Okay, in this clock cycle, what's going on? First of all, if we go back to program, before starting to execute this program, at this point, what is the value of a PC program counter? Which value is like in the program counter? Who can tell me? Just write the answers. It doesn't need any calculations, so you need to respond. You can respond promptly. Very good. I got one answer, but I need more answers. You know, just one is not enough. Well, yeah, I've got the second answer. So what's the definition of program counter? A program counter always holds the address of the next instructions. Very good. I got several answers. So at this moment, the program counter holds the address of the next instruction, which is 100. Very good. So the value of the program counter is equal to 100. We don't know what is the value of IR, MAR, MBR, and AC, so we don't care, just we put dashed lines. It means that we don't know what are the values of those numbers. The next instruction, the next part is like fetching the instruction from the memory. How we can fetch the instruction from memory? The first thing we should do is placing the program counter to MAR. Placing the program counter to MAR. So MAR will be equal to 100. Okay, MAR will be updated to 100. The next step is like fetching the instruction. All of these lines, these 4 lines, sorry, let me just go back to all of these 4 rows, sorry, for all of these three are the fetch cycle, okay, fetch cycle. So in the next time clock, which is time clock 2, the content of the memory with the address MAR will be loaded to IR. Let's go back to our program. What is the value of this address? The value of this address is 1104. So this value will move to the IR. So IR will be equal to 1104. Now IR has like the instruction. The last step in the fetch cycle is incrementing the PC, the program counter. And now the program counter is pointing to the next instruction. So 100 will be updated with 101. So now the program counter has a value of 101. Next cycle, the next phase is decode phase. The decode phase, which consists of these 2 cycles. In the first cycle of decode phase, bits 0 to 11 of IR, bits 0 to 11 of IR, which is the address, will be moved to MAR. So MAR at this time will be 104. MAR will be 104 because we need to load the content of this address. And in the next cycle of the decode phase, which is time 5, T5, the instruction will be decoded. What does it mean? It means that the control unit will check the opcode, and at this moment, after checking the opcode, the control unit knows that the instruction is a load instruction, and based on that generates the signals. And then we get the operand from the memory. How we can get the operand from the memory? So we have the address of the operand, and we place it in MBR. What is the address of operand? The address of operand is 104. So the processor checks the address 104 to see which data is located in 104. The data in 104 is 0023. So this value will be loaded to MBR. At this moment, MBR has the value. And the last step is execute step, which MBR will be moved to accumulator. So MBR will be moved to the accumulator. And so after running these 8 cycles, if you check the result is here. It's the accumulator which has the number 0023. Let's go back to our program. In our program, if we look to the program, what does load 104 says? It says that go to address 104 and put the value in the accumulator. We did exactly the same thing. Okay, we did exactly the same thing. Any question? So what I want you be able to do is just completing this kind of tables. Okay, so we need to write the machine code and fill this table. Let's move to the next instruction. What is the next instruction? Of course, the next instruction is add 105. What does add 105 say? Add 105 says that get the data in address 105 and add it by the accumulator and place it in the accumulator. Let's see. Here is like the RTN for add 105. So at this moment, let's check the initial values of the registers. At this moment, the initial value of the registers are not unknown like the previous slide, because the last cycle of the previous instruction, the load instruction, updated these values. And so these values are the initial values for the next instruction. So these values, the last values of each instruction, is the initial values of the next instruction. So if we move to the next instruction, the initial value will be these values. If we look, we see that the initial values are same as the last values of the previous instruction. Okay, any question? So let's start again with the same story. So let's just fetch. For fetch, PC will move to MAR. So PC is 101, will be like changed to 10. It's 104, will be changed to 101. The next instruction says that the content of the address of 101 moves to IR. So what is the content of the address of 101? Let's look together. What's the content? The content of address 101 is 3150. 3105. 3105. So 3105 will be placed in IR. Okay, will be placed in IR. So at this moment, IR has the instruction. Then the last step of fetch cycle is like increasing the PC by 1. So the PC at this moment is pointing to the next instruction, which is 102. Okay, we're done with fetch cycles. Questions? No question? Okay. Okay, let's move to time 4. At time 4, we'll start decoding the instruction. The first thing we do, we place the address field of IR, to MAR. The address field of IR to MAR. And so address field of IR is 105. Address field of IR 105 will be placed in MAR, not the entire IR, because IR, if you remember, was 16-bit and MAR was 12-bit. So the address field, which is 12-bit of IR, will be moved to MAR. Any question? Okay, now that we have the operand address in MAR, the control unit decodes the instruction. It doesn't change any value in these registers. Just decode the instruction to see what kind of signals it's supposed to be generated. So, and after that, the processor gets the operand from address 105. So the content of address 105 will be moved to MBR. What was the content of address 105? Of course, if you remember, the content was FFE9. FFE9. Now that we put this value, we add those two numbers together. Okay, we add those two numbers together and see what's going on. So the next step, the accumulator and MBR will be added together, and the result will be placed in accumulator. Okay, the result will be placed in accumulator. Any question? Okay, let's go back to previous slide. I believe that this one shouldn't be 0C. It should be 0 because it's negative 3 plus negative 23 plus 23. It's 0. Let me check the textbook quickly. I'll let you know. Just let me check the textbook. Oh, one thing that I noticed here, let me just tell you what's going on here. These numbers, when we go back to this slide, these numbers are not in are not this 23. It's not in decimal. It's hexadecimal, the hex number. So I thought that it's like decimal. So I said that 23 plus, because this one is negative 23 in decimal. In decimal, it's negative 23. And I said that, okay, so 23 plus negative 23, it's equal to 0. But I noticed that this 23 in the in address 104, it's not decimal, it is hexadecimal, but it didn't mentioned in the in the slide. So it's the reason I said it should be equal to 0. So because that one is hexadecimal, the total of those two numbers will be equal to 000C, not 0. Okay. Now let's any question? Now let's move to the next instruction. Next instruction is what was the next instruction? Is a store instruction. Okay, let's do the store instruction together. And because I don't have it in a slide, I need to do it on OneNote. Okay. Okay. Uh, I had a question on the quiz. Would you ask us to fill out the entire table with certain columns? If you win the quiz next week, this is not part of the quiz next week. The quiz next week is up to the interrupts, which I will tell you which slide is that. But in general, in any other quiz later, it might be like like few cells from each columns, okay? And the other question I got is which page is it on? If you have the textbook fifth edition, it is on page 251, page 251. And if you have other versions of version 4, it might be like in a page, maybe a few pages, like before or after 251. Okay, so let's just complete the table for stall 106. Stall 106. My God. Just I'm drawing the right table for the instruction stall. How many rows do we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So here is accumulator. Here is MBR, MAR, IR, PC, and RTN, and step. Okay, so okay, first let's check initial values. Initial values. So those initial values coming from the last step of previous instruction, which was at 105. So PC had a value of 102. IR has a value of 3105. MAR has a value of 105. MBR has a value of FFE9, and accumulator has a value of 000C. Okay, all these numbers are in hexadecimal. So the first step is like for fetch cycle or fetch phase is placing the PC to MAR. So MAR will be, let me just, for new variable, I 102. So MAR will be updated to 102. The other values are the same. The next step is just transferring the data at the location of 102 to the IR register, So PC still it's 102. IR register will be updated. What is the hexadecimal value in 102? If we go back to our instruction table, we will see that the value was 2106. So 2106 will be moved to IR. MAR is still 102. MBR it's FFE9, and accumulator it's 000C. So at this step, the IR was updated. Okay. The next step is updating the PC. So PC will be incremented by 1. So the PC will be 103, and the other registers will keep their own values. So PC has been updated. Okay, so we're done with fetch cycle. So next cycle is decode cycle. So decode cycle starts here. In decode cycle, the IR sends its data from bit 0 to bit 11 to MAR because it is the address of the data. So PC will be remain 103, IR will be 2106. The first 12 bit of IR definitely is 106. 106 will be moved to MAR. MBR still is FFE9, and accumulator it's 000C. So which register updated? MAR was updated in this step. Then at the next step, the instruction will be decoded. Okay, the instruction will be decoded. So decode IR 15 to 12. So decode to see what kind of instruction is that. So what should the processor does? So no change in the variables. Okay, so do you guys still hear me?
Yes.
Oh, good. I got a question here from one of you. It says that, so what exactly does MMAR mean? I will answer after finishing this table. I will answer to that question after finishing this table. Okay, so decode IR. So the IR is done, and we in the next step we need to get the operand. So get operand, PC it's the same value. In fact, at this moment, because there is no operand being get from being got from the memory, not necessarily. This step is not necessary. Not necessary. Why? Because for restore instruction, we don't need to get operand. So this step, there's nothing going to happen in this step because there is no operand we need to get from memory. Next step is execute phase, execute. In the execute, the accumulator will be moved to MBR. So PC still is 103, IR is 2106, MAR is 106. and MBR will be 0006 because accumulator has been like moved to uh, MBR. And the last step says that MBR moves to the address which is defined by MAR. So again, no change in the registers, it's same. But what's going on in the last step? The memory location of 106, the memory location of 106 will be updated by the value of 00C. The memory location of 106 will be updated by the value of 0006. Okay, so any question for this table? I already have one question, which asks what exactly does MAR means. Okay, but other than that question, so is there any other question? Okay, so to answer the question, what does MMAR means? I uploaded the video on my on the Sakai, so you can access to that. And I see the same person. No, I don't know if it's the same person or not, but I see that just says that so MMI just means the memory location for MAR. Yes, it doesn't mean the memory location. It means the content of memory location, the content of memory location with address MAR, the content of the memory location with address MAR. Okay, so if this is a memory, and the memory starts from address 100, 101, 2, 3, and each cell has like an information A, information B, information C, D. If I say M102, I mean the data C. If I say M100, I mean data A. Okay, so these addresses 102, 100 are in the MAR register. So MAR register determines the address, and MMAR determines the data which is located at that address. Is it clear now? Just okay. So MMR is the content of the memory at address MAR. The content of memory at address MAR. Let's go back to our our table. For example, at I told let me use a different color for my highlighter. So for example at this point, I said that MAR is 102, and when I say MAR and MMAR, I mean that the content of the address 102, which is 2106, moves to IR. So we see that 2106 moved to IR. Okay, so that one is like the content of it. Okay, so now that we're done, we see that the sum of the two data in the two different memory locations added together and placed in address 106. Okay, any question? Okay, if there is no question, let me just go back to the slide. Okay, let's go back to the slide and start the next part, which is a discussion on assembler. Okay, what is assembler? If you remember that hierarchy, that pyramid that I showed you at the beginning of the semester, like the first 2 weeks of the semester, and it had like different levels. The like the highest level was user like language, and the lowest level was gates and like electrical circuits. And we had in the middle of this pyramid, we had several layers like assembler and compiler. What does compiler do? The compiler translating the program from high level language to assembly language. So compiler convert the language from high level language to assembly language. So no matter if you write a program in Python or C, when you compile them, some of these programs are not like a compiler, but just in general. I'm talking in general. If we writing in two different languages and we compile them, regardless of the language, the output will be same. Output will be same. The compiler just convert different high level languages to a same assembly languages. Okay, so this one is about the compiler. What does assembler do? Assembler translates the assembly language to machine language. What is machine language? Let me go back and show you what is machine language. Okay, let me just go a few slides back. Okay, here. Okay, assembly language is here. Okay, these are assembly languages. And machine language is like these numbers, these like these numbers, and of course these micro operations. Okay, all of them are in machine language level, and it's like the definition of instruction set architecture. So it translates the assembly language to machine language. Okay, so now we like the input of an assembler, which is in assembly code, is called source code. And after converting to machine language, we call it object program. Okay, so object program is like the output of assembler, which is bunch of zeros and ones. But how we can how does the assembler convert the source code to object code? It like uses a symbol like table to do this conversion. Okay, let's take a look together and see how does it work. First thing I want to tell you, I prefer to use my OneNote for this part of the lecture. Okay. If you, I'm sure that all of you or most of you have like coding experience, and you have written some like programs, maybe complicated, maybe simple programs. And for all of those programs, if you know, none of us determine or like write the program by writing the physical address of memory. We usually use labels. Do you remember when we have like when we have uh, when we have a program like let me just write it here. Let me make it like better. Just okay. I'm going to write a program here for you. Here is hex address, and here is instruction. When I write a program, I say load X. Okay, I don't know what's the location of X. And then what do I do? Like I would say, okay, label X has a value of FFE9. And then I say add Y. And I say, okay, label Y is a location of memory with address, let's say X become address 0023 and Y address FFE9. And then I say store to address Z, and we say address Z like as a content of 00 at this moment. And finally, we say halt. Okay, we write our program in this way. We don't care about the actual address. We write the program. This what you see here is like an assembly program. We say load X, add Y, store Z, half. X has a value of label X has a value of 23. Label Y has a value of FFE9, and label Z, which will keep the final result, has a value of 0. When we load this program in a memory, it will be located in a specific memory address range. Let's say load X will be placed in address 100, add Y will be address in 101, store will be uh, placed in address 102, half will be stored in address 103, label X, which has a value of 023, is an address 104. Label Y, the like will be in address 105, and Z is address 106. So this one is our program located on the actual memory. So at this moment, we have the instructions placed in the memory. Now we want to find the machine language. The assembler needs to find the machine language. The assembler translate this program to machine language in two passes. Two passes. In the two passes. Okay, in these two passes, in the first one, it does the half of the job. In the second one, it does the rest of the job because it can't do it once. Okay, let's see how does it work. The assembler, in fact, builds two tables. Two tables like this and like this. Okay. And after that, it starts to investigating the program line by line. It starts from line 100. In line 100, it says that the program. Let me double check my note. Okay. In address 100, it's load. What is the opcode of a load instruction? You remember the opcode of load instruction is 1. So it says that the opcode of load instruction is 1, but the address is X. I don't know what's the address because the assembler just investigating this line. It doesn't have any idea about this part of the program yet because it moves line by line by line. So when the assembler starts from address 100, it doesn't know anything about the actual location of X, Y, and Z. The only thing it knows that the instruction is the opcode is 1 and the label is X. Then it moves to the address 101. It says that it's the add instruction. Add instruction has an opcode of 3 and the address is still known. Okay. Move to the next instruction. Next instruction is 102. It's a store. The store has the like opcode of 2 and address is ZZZ. The next instruction 103 is halt. Halt is opcode 7 and the address is 000 because halt doesn't have any like address field. It's 0. So when it reaches to this point, it continues. Moves to the 104. At 104, it says that X is equal to address 104, hexadecimal. Y is the address of 105 and Z is address of 106. Okay, then it completes this table. So this is the first table completed. This one is the second table completed. Those 0x means that the numbers are in hexadecimal format. Okay, so 0x means that. So when we reach to this, when the assembler reaches to this point, at this moment, like it updated the table 1 using this symbol. So instead of x, it plays 104. Instead of y, it plays 105. And instead of 6, it plays 106. So at this moment, the table which contains the machine language will be equal to 1, 104, 3, 105, 2, 106, and 7000. And bingo. This one is like the machine language for the program. Okay, so this one is the way that assembler converts the assembly language to machine code. Why it doesn't do it at the same time? Because the assembler starts from address 100 and move line by line. So it needs to like first complete this table in this form, then find the like the symbol table, and then update the table 1 with the actual machine language. Is it clear? Okay. Do you guys hear me? Just a confirmation. You hear me? Oh, okay, good. So let's go back to our PowerPoint. Okay. One moment, please. Let me connect the charger. Okay, so this slides like explaining the same like concepts that I already discussed. So here is the same thing that I explained. And by the way, the thing that I should also mention is when we have some programs in the data, it is supposed to mention if the numbers are decimal or hexadecimal. Do you remember that 23 that I said it's like we thought that it's decimal, but it was hexadecimal. If we convert it to decimal, the number will be 35. Okay, so be careful about these like notations. for the number systems if they are given to you by decimal or hexadecimal. And this one is the second, the same slide. We continue. And here is extending our instruction set, which I will stop at this point. So it's enough for today, and we will talk about extended instruction set next Tuesday. Okay, so before you leave the meeting, let me tell you a few things. First, next Tuesday we meet in class, physical class. Second, we have a quiz at the end. We have a quiz or test at the end of the class. I give you 30 minutes, but if you need extra time, I give it. I just you have it. Okay, so you can sit in the class after the class time, and if you need extra time, so don't worry about the timing. Uh, so the next thing for your grades of exam 2, I will check your grades. I will check your uploaded drafts for confirmation and compare them with your grades and update the grades. I will let you know when the grades are finalized. And the next thing, I already uploaded the video of my last lecture, Tuesday lecture on Sakai today, and I will upload this video like in an hour, and so you can access to these videos. Don't forget to accessing these videos. You need to go to the lesson, not to the resources. And if you have any concern, any question, please feel free to contact me. Okay. Uh, Let me stop the recording and then